Okay, so what we're talking about today is we're talking about what are called extrema. I guess that's not written anywhere on here. Maximums and minimums, or I guess the real plural would be maxima and minima, but that's kind of, I don't know. We call those extrema. And we're also going to be looking at intervals of increasing and decreasing. I think you guys might have looked at all of this last year, potentially, maybe. Absolute maximum. Did you guys talk about that last year? Mm-hmm. Okay, sweet. Relative maximum. Okay, good. We're just going to look at it a little more specifically. This is a huge, huge topic in calculus. Calculus is basically analyzing graphs to try and find this stuff and like interpret it in context. Usually like real world examples. So calculus is pretty focused on this stuff right here. So first of all, there's a couple different names that we can refer to these by. So Delta Math likes to use the word global maximum or minimum instead of absolute. I usually use the word absolute. In calculus, we tend to use the word absolute, but they really mean the same thing. An absolute max or min or a global max or min is the greatest value that a function assumes. I might even use the word attains here. Doesn't matter. Synonyms in this case. And this is usually on a closed interval. We'll look at some examples to see what I'm talking about. We usually ask about this on a closed interval. But it's the greatest value. So when we say the greatest value that a function attains or gets to, would we be talking about the y values or the x values?
Y values.
The y values, yes. So anytime we're talking about something the function does, we are talking about y coordinates. This always answers the question, what? So if I said, what is the absolute maximum? You should give me the biggest y coordinate. Anytime we talk about intervals, we're talking about x coordinates, and this is going to answer the question, where? This is something that I've mentioned before, but I think it's very helpful. So if we say the function is increasing, that means the y values are going up. When I ask the question, where is the function increasing? Your answer should be x values that describe where the y values are going up. So an absolute max or min is the smallest or the greatest y value that a function attains, period. Think of like the tallest person in the world, the absolutely tallest person, the globally tallest person, like tallest person in the world. Whereas when we say a relative maximum or minimum, it's basically the largest or smallest y value, like in a small area. But what we say is the definition here is when a function changes from increasing to decreasing. So it's like if we were looking at like the weather for today, it gets warmer throughout the day, the temperature is increasing, and then at some point it starts decreasing. That point where it starts decreasing and stops increasing, that would be the relative maximum temperature for today. Would we say that that's probably going to be to like today's high? Is that probably going to be the absolute maximum temperature of the year 2025? I doubt it. That's probably going to happen later, probably in July, maybe August. Probably not right now, but that's the difference between it. But it's a change from increasing to decreasing or decreasing to increasing. So when we look at a graph here, first of all, if we're looking at an open interval, which means there's no endpoints here, like in number 1. We're just looking at this whole dang function as it goes from negative infinity to positive infinity. And we see on the ends of that graph, like both ends of the graph are pointing upward to positive infinity. So what we would say here is there's no absolute max. We are growing forever. We are never going to reach an absolute maximum value. This graph does have an absolute minimum value. What is the absolute minimum value of this graph? -3 is correct. It happens right here. And so notice the minimum is the y-coordinate. I'm going to add a little column here that says where. So we're going to say at x equals -4. It is not correct to list the coordinates of the point and say, oh, the absolute minimum is -4, -3. Wrong. The absolute minimum is -3. And that happens at x equals -4. Okay. So we have a few relative extrema, maxes and mins. The relative maximum is what? 2. And where? Yeah. And we want to make sure we say at x equals 1. This is our relative max. And how many relative minimums do we have? Yeah, we have dose. 1 is the absolute minimum, which we already said. We have -3 at x equals -4. And the other one is -1 at x equals 3. Right there. Okay. When we look at increasing and decreasing, we always read from left to right. And so we look at where the y values are going up as we read from left to right. So increasing intervals would be here and here, similar to positive slope. We don't want to say the slope is positive because it's not a line, it doesn't have slope. But those red regions right there, those are the intervals where we're increasing. And so since we're saying intervals, we're going to give x values. And we're going to say from -4 to 1. And then we're going to say from 3 to infinity. For increasing and decreasing intervals, you can actually use brackets or parentheses. Brackets are technically more correct, but for our class, even for AP Calculus, you can use either one. The only thing is you can't use brackets with infinity, ever. Parentheses. This is actually like a point of discussion in the math world right now and over the last few years of like what's more correct, parentheses or brackets. So you might see some old textbooks, or sometimes Delta Math uses parentheses. Delta Math will actually accept both answers. It'll accept brackets or parentheses, and that's fine. And I will too in calculus. We accept both. What you don't want to do though, just don't do brackets for one and parentheses for the other. That's weird. Don't do that. So just be consistent. But brackets are more correct. And then for our decreasing intervals, those would be here and there. So similarly, we would say -infinity to -4 union 1 to 3. So I'm using brackets for the numbers and parentheses for infinity.
So you can use brackets on like the increasing and the decreasing?
Yes. Yes, exactly. And the explanation for that is, this is literally the explanation that they use for that. If I stand here in the doorway, am I in the room or in the hallway? The answer that they would argue is both. I'm both in the room and I'm in the hallway. And so the bracket's like, are we increasing or decreasing at -4? There's an argument for neither, there's an argument for both. The brackets argument says, oh, it's both increasing and decreasing at that point, it's changing. So, yes.
I think I heard this from somewhere, but if there's like no absolute max or like it goes on forever, will we pick the next highest point?
Well, if we are going up for forever, what is the next highest point? Because if we're going to infinity, there's a point that's 1 million, there's a point that's 1 trillion, there's a point that's 1 quadrillion. So there's no. So are you saying like maybe we would pick that instead?
Yeah.
Yeah. The only problem with that is like there's all these y values that are already higher than that, let alone all infinite of those, and all infinite of those. So we would say there's no absolute maximum because we are increasing forever. Yeah. Okay, you guys do number 2. All right, so does this graph have an absolute maximum or minimum? No, it does not. So that is none for both of those. What is the relative maximum? 3 at x equals -4. Nice. Relative minimum. Nice. Okay. Increasing from -infinity to -4. Union 1 to infinity, and decreasing from -4 to 1. Okay, notice too that like if we have a maximum at -4, -4 is where we are going to change from increasing to decreasing. So like our x value should match that. So if our maximum is at -4, notice we increase until -4, then we start decreasing, and we have a relative minimum at x equals 1. So x equals 1 is where we change from decreasing to increasing. So all those x values should kind of match. We just have -4 and 1, and we have -4 and 1 for all of those right there. So they should all match up. Okay, in this graph right here, do we have an absolute maximum?
Yeah.
Yes, we do. What is it? 6. Okay. 6 at x equals that's -7. Thank you. That is hard to count. A lot of boxes and squares in there. Do we have an absolute minimum?
Yes.
Yes. What is it?
6 at x equals 4.
Nice. Okay. I want to point something out. This is definitely a relative max right here. This is definitely a relative minimum. What do you guys think? Is this a relative max? Turn to your neighbor. What do we think? Okay, thumbs up for yes, it is a relative max. Thumbs down for no, it is not a relative maximum. Thumbs up or thumbs down? Okay, the correct answer is no, it is not. Abby, why'd you have your thumb down?
I don't know. It's different from like the other graphs.
Okay.
And because it's like already the absolute max, like I don't know. It just didn't seem like it.
Okay, fair, totally fair. This point right here, in the first one, this was both a relative minimum and the absolute minimum. So points can be both. But I think the first part you're saying where it seems different than the other ones, I think that's closer to why. Can anyone explain why this is not? Well,
Because there's not like a thing behind it.
there's not a thing behind it. Okay, what kind of thing would we want to see over here? What would we want to see the graph doing?
Like an increasing slope.
Like that? Or sorry, increasing slope, so like that.
Yeah.
We would want to see, okay, so we would want to see the graph change from increasing to decreasing. That's correct. So the graph does not change from increasing to decreasing. And so similarly, this point is not a relative min. So we need to see that kind of valley shape or peak shape in order for it to be a relative maximum or minimum. So our only relative maximum would be 4 at x equals 1. Our only relative minimum would be -3 at x equals -3. And then it looks like we're increasing from -3 to 1. And we are decreasing from, not negative infinity, from -7 to -3. One, 4. Okay, we'll do one more here. What I'm going to do is I'm going to change this graph for number 4. I'm going to say our graph goes up here. To that dot, whatever that is. 1, 2, 3, 4, 5, 6, 6. And we'll say this one comes up here to 7. Okay, you guys do number 4. All right. Check with your neighbor. See what they got. Okay, so absolute maximum is what's the absolute maximum? 7. Yes. And that's at x equals -7. Okay. What is this point right there? Is that absolute max or relative max? Neither. Yeah, neither. Yeah. Nothing. Okay, it's just a point up there. Absolute minimum is
0 at x equals positive and -4.
yes. Nice. Mo, technically I answered your question wrong before. There is just one absolute minimum. it is the number 0. It's the smallest y value. It occurs at 2 places, but we would say there's 1 absolute minimum. There are 2 relative minimums, because there are 2 places where the graph changes from decreasing to increasing. And those are both a 0 at x equals positive or negative 4. But there's technically only 1 absolute minimum. That's the number 0. It just happens twice. 2 places where the graph changes. That's more getting into the weeds. You don't really need to know that. How many relative maximums do we have? 1. And what is it?
4 x equals 0.
Yeah. Nice. Okay. So then we are increasing from where to where?
4 to 0. 4 to 6. Or 4 to
I think it's 7. Yeah. Right. 1, 2, 3, 4, 5, 6, 7. Yeah, 7. Yep. And then so decreasing would be from.
I have a question.
Yeah. What's
Why
up?
isn't that point the relative maximum the one on the top one?
Oh, this one here. This it doesn't change from increasing to decreasing.
So it just like gets nothing.
Yeah, I guess nothing. Yeah. Okay. So it would be decreasing here from -7 to -4, and from 0 to 4. Okay. Any questions about that stuff? Okay. Like I said, in calculus, we do a lot of analysis of graphs this way. If you guys go to the next page. This is not really an AB calculus question. This is the graph from an AB calculus question, but the rest of the question is not the same. But this is one that we use in calc. This is a problem that represents the number of phone calls that some company is getting per hour. And so this is like the rate of people per hour that are calling in and how it spikes. So if you take those of you guys that are taking AB calculus next year, you'll see this graph again. But the reason that we learn stuff like this is to analyze graphs like this to find out if we have some sort of measurement of like people per hour or like the flow rate of water or electricity. We can use that to then analyze like, okay, well, what was the time when the most number of people were like waiting on hold? Or how many gallons of water were pumped into the tank over this time? And so that's like all the kind of stuff that we learn how to do in calculus. What was the maximum amount of water in the tank? Things like that. But for this question here, we're just looking at this graph. And yeah, I want you guys to take a couple minutes and do all 6 of these questions based on this graph right here. Ready, set, go. All right, guys, let's check this. So we are increasing from 0 to 2. That's it. And we're decreasing here from 2 to 4 and from 6 to 8. And we're doing neither from 4 to 6. We have constant slope. We have no local minimum because the graph never changes from decreasing to increasing. So that's what we always have to look for. Decreasing, then increasing afterwards. That's what gives us a local minimum. So that can be something that's kind of hard to remember, but that's like the very strict definition. Changing from decreasing to increasing, or increasing to decreasing. We do have a local maximum at t equals 2. So make sure your answer for this is t equals 2 because of what the question is asking. At what value of t is there a local maximum? t equals 2. Yes, the local maximum is 1200, but that was not what the question was asking.
Why isn't it 1,000? Like, isn't
That's like
t equals to like the absolute maximum?
Well, it is the absolute maximum, yes, but it's also a relative maximum because it changes from increasing to decreasing. Hey. Grab the notes on top of the pink poster there. Okay. Average rate of change. Did anyone figure out or have a good guess of what they think this means?
I just did like negative 1,000 over 8, since it changes 1,000 and did it over 8, and then that simplifies to negative 125 over 2.
Yes, that's correct. Yep. So another way of saying the average rate of change is saying the average slope from t equals 0 to t equals 8. And so, yeah, our slope goes from here to there. And because we're going from 0 to 8, yeah, it's just down 1,000 over 8. But you could think of this as like 1,000 minus 0 over 0 minus 8. Negative 1,000 over 8. And that's negative 125 over 2. Yes. Or is it just equal 125? Negative 125.
Yeah, I'm just doing that again.
Okay. Yeah, because 1,000 divided by 4 is 250.
Yeah,
Yeah,
I did that.
that's all right. So we would say the average rate of change is negative 125. Yeah, this is something we look at a lot in calculus, the average rate of change. It's just saying the average slope between 2 points. So y minus y over x minus x. Okay, r of 0 is 1,000. Just plug in 0 for x. See it on the graph right there. R of 3 is 800. Find t when r of t equals 100. We might have to guesstimate there a little bit. It's like right there. 7.5. That's a pretty good guess, halfway in between. When we write the piecewise equation in the next step, we can double check that we got that right. For the piecewise equation, be careful because the slope here is not up 1 over 2. It's not 1/2. Okay. Because we're going up how many? 200 and then going over 2. So 200 over 2 is 100. Yeah, so just be careful. Don't let the boxes trick you. The slope here for this, so we'd say m equals 100. The slope here, we're going down 800 over 2. So our slope is negative 400. Our slope here is negative 200. So just got to be careful. So here's what I got for the piecewise. Bless you. So the first part is 100x plus 1,000. This second part here, I did this in like transformation form. I didn't really want to figure out what the y-intercept was. So I just looked at this point right here, which is to the right 2 and up 1,200. And then I used the slope right there. Yeah,
When writing piecewise functions, does it have to be labeled like in order?
Yes. It does. And something I noticed with this, our variable is not x. Our variable is t. So we should be using t. I make my t's a little bit curved so that they don't look like plus signs. So if we did the y-intercept, it would be what, like 2,000? Negative 400 t plus 2,000. Then we just have y equals, or r, I guess r equals 400 for 4 to 6. And then the last part is negative 200t plus 1,600. That one I was able to kind of just count the boxes up and figure out where it would hit. Remember, for like t equals 2, we want to have one of those be equal to 2 and one of them not be equal to 2. So it doesn't matter which one the equal sign is on as long as it's on exactly one of them. Same thing with 4, same thing with 6. So we can't do that. That would be wrong. Okay, if we want to double check this one right here, oops. We could set r of t equal to 100, which is going to happen over there. So that's this part of the line right there. So if I said 100 equals negative 200 t plus 1,600, when I solve for t, I think I will get 7.5. So I subtract 1,600 from both sides. I get negative 1,500 equals negative 200 t. Divide both sides by negative 200. And so that's the same as 15 over 2, which is 7.5. So that's just double checking that one. We're going to use this piecewise equation as well to find these other things that we're looking for. Just going to erase all that. So I'm going to plug in 1.5 right there. 100 times 1.5, because that would be, it's kind of hard to just figure out from the graph. Plus 1,000. So that'd be 150 plus 1,000. I'm going to plug 6.75 into that one right there, because that's where t equals 6.75. So 6.75 times 2 would be 13.5. So 6.75 times 200 would be 1350. So negative 1350 plus 1,600 is 250. Which one of these equations should I use for when r of t equals 625? First, second, third, or fourth? When's r going to equal 625? First, second, third, or fourth? Yeah, second one. So 625 is right here. So what we're going to do is say 625 equals, and we'll set it equal to that one right there. Negative 400 t minus 2 plus 1,200. So 625 minus 1,200 would be negative 575. Right? Is that math that good? Divided by negative 400. So it's going to take a little bit of simplifying here. So 575 and 400 both obviously divide by 25. That goes in twice. So it's 23 over 16? 23 over 16. And that equals t minus 2. So then I just add 2 to that, which would be 32 over 16. So that would be 55 over 16. T equals 55 over 16. Yes, I can double check that on Desmos here. We've got y equals 625, and we've got y equals negative 400, x minus 2 plus 1200. Let's see, let me change my y-axis there. It's so small I can't see it over there. $3.4375. Is that 55 divided by 16? Yes, it is. Okay, that's the answer we should get. Be ready to do math like that. Okay, you guys can go back to your seats, and we'll finish up here. Okay, we're going to do a quick review of our different types of discontinuity. Kind of mentioned these last time, so we'll be able to go through this pretty quickly here. We've got 3 types of discontinuity. And these are the kind of things you see in piecewise functions all the time, or functions in general. We have infinite discontinuities, which are vertical asymptotes. And this happens whenever we divide by 0. So letter A here is just our parent function shifted over 2. So we have an infinite discontinuity right there. And we know that before we even graph, because we can see x minus 2 on the bottom there. Notice similarly to before, we're saying like the x value is telling us where this is happening. So it's, what do we have? We have an infinite discontinuity. Where is it? At x equals 2. X marks the spot. And this one we can see we have one at x equals 4. A removable discontinuity is a hole in the graph. This occurs whenever a factor cancels out from the top and bottom. So we would say we have a hole or a removable discontinuity at x equals -3. The resulting graph would look just like this. It would look like x minus 3. Slope of 1, y-intercept of 3, but there would be a hole at x equals negative 3. In letter B, we would say we have a hole or removable discontinuity at x equals 1. The difference here is what we're saying is there's just one y value missing. Or we could say just one point missing. Okay, then we have jump discontinuities, which occur in piecewise functions. It looks like that there when the two ends of the graph don't match. So we could say this is when two sides of a piecewise approach different y coordinates. If we just have the equation, here's how we would see that. We take negative 1 and we plug it in for x in both of them. So 2 times negative 1 plus 1 is negative 1. This is where our closed circle is. Negative 1 minus 4 is negative 5. This is where our open circle is. And we can see that those don't match. So we'd say we have a jump at x equals negative 1. Same thing that's happening in this picture right here. We have a open circle at 3, closed circle at 1. They're not in the same place. This is discontinuity. Okay. On the next page here, I want you guys to do numbers 1, 2, and 3. All right, let's check. Number 1, do we have a discontinuity here? Yes. What type? Yes. It's not wrong to say we have a vertical asymptote as well. You could call it infinite discontinuity. You could say it's a vertical asymptote. And we want to say where it is. Where is it? Yes. Okay. Number 2, do we have a discontinuity? Well, 0 squared minus 1 is negative 1. 2 times 0 squared plus 3 times 0 minus 1 is negative 1. This is continuous. Since our closed circle and open circle end up in the same place, the graph just keeps on going. Hmm?
How is 1 minus 1
Hmm?
negative? Or how is 2 minus 1 negative? Is there anything?
2, it's 2 times 0 plus 3 times 0 minus 1.
It's not 2 times 0 squared.
Well, 0 squared is 0. So it's still 2 times 0. So that'd be 0, 0, minus 1, 0, minus 1. Okay. Number 3, do we have discontinuities? How many? So did you guys factor this? X plus 1, x plus 2, over x plus 1, x minus 1. So this means we have a what? Where? Yeah. Whole or removable discontinuity. I'm always writing whole because it's way shorter than the word removable. Is there another discontinuity?
Yeah.
Yeah, what is it?
Infinite.
Yes. Yes, we still have that. These are just like those graphs we did back in September, October. You know, we've got our x-intercept, our vertical asymptote, our y-intercept. Got a hole in the graph here at -1. Oops. Something like that. Horizontal asymptote is 1. So this is our whole unit 2, graphing rational functions. Now we're just talking about the discontinuities specifically. Okay, just to review some other things about functions. We want to just remember our end behavior. This will help you graph like x cubed and x squared, those parent functions as well. So if we have a positive odd degree, function goes like that. Remember, we want to say the limit of f of x as x approaches infinity is infinity. Sorry, that's the left-hand end behavior. Let's move that down here. Okay. And the right-hand end behavior, sorry, the left-hand end behavior would be as x approaches negative infinity. We're going to negative infinity. Our next unit is what? Limits. So this is a little preview. When we flip it, it goes in reverse. And here's our positive even and our negative even. The nice thing about these is the two sides, the two end behaviors are the same. So we could say the limit as x approaches positive or negative infinity of f of x equals positive infinity. And here we could say the limit as x approaches positive or negative infinity of f of x is negative infinity. A little bit less writing for that one. So it's hard to do a whole unit on functions without talking about end behavior like we talked about earlier, without talking about discontinuities. We're kind of seeing all that stuff. But mostly just want to keep that stuff really fresh. We're in the pre-calculus section of pre-calculus. I know that sounds like we would be in it the whole time, but we're not really. Now is the pre-calculus part. So all this stuff's really, really important. We have a quiz next class.